Welcome to this explainer. Today, we are taking a seriously fascinating journey under the hood of the Hugging Face Transformers library. If you've ever wrangled with natural language processing or modern machine learning, you already know the drill. Managing models with billions of parameters can be, well, an absolute logistical nightmare. Yet, somehow, this ecosystem makes it look incredibly easy. So we're going to uncover the hidden mechanics behind loading massive AI models using literally just a single line of code. So let's dive right in and pose the central mystery here. What exactly happens when you run that famous from_pretrained command? To the user, it's just completely seamless, right? You type one line, press enter, and boom, a state-of-the-art model is sitting in your computer's memory, fully ready to generate text, classify images, or translate languages. But beneath that one tiny line of code is a crazy sophisticated system of architecture detection, memory management, and dynamic transformations. Think back to the old days, or really just life without this library. It's fascinating to compare hard coding a specific model architecture versus using dynamic loaders that adapt automatically. Before, you'd have to manually import the exact class for the model you wanted, like a specific BERT or GPT architecture, and if you wanted to switch models, yeah, you had to rewrite your code. But Hugging Face introduced AutoClasses, which act as dynamic model loaders. You just hand it a checkpoint name, and the library reads the files, figures out the architecture, and instantiates the correct class for you. It keeps your code super clean, flexible, and totally agnostic to the specific model running under the hood. So here is our roadmap for today. First, we'll look at the magic of AutoClasses. Second, blueprints, the model configuration. Third, heavy lifting, loading weights. Fourth, dynamic weight transformation. And finally, saving and sharing models. All right, Section 1, the magic of AutoClasses. What's really wild here is how each specific autoclass attaches a unique task head to the base transformer. You see, an AI model usually has two main parts: the base model that understands the data, and a head that actually performs a specific task. AutoTokenizer handles converting your text into numbers. AutoConfig loads the settings, but look at the models themselves. AutoModel just gives you the base transformer, outputting raw hidden states or embeddings. But if you use AutoModelForSequenceClassification, the library automatically takes that exact same base transformer and just snaps a classification head onto it, instantly preparing it for tasks like sentiment analysis. It's like a giant puzzle. We see this confusion all the time. Here's a fantastic question from a Reddit user that perfectly highlights a real hurdle when you're first exploring the Hugging Face ecosystem. When you're browsing through documentation or looking at code snippets on GitHub, you will constantly see AutoModel used in some places and AutoModelForCausalLM used in others. So why the distinction? What actually happens if you use the wrong one? Here's the deal. The crucial point is that AutoModel gives you the raw embedding skeleton, while AutoModelForCausalLM adds the necessary flesh to actually generate text. If you just load AutoModel and feed it a sentence, it spits out dense mathematical representations, embeddings. Totally useful for sure, but definitely not readable text. But when you initialize with AutoModelForCausalLM, it adds an additional linear network layer right on top of those embeddings. That layer maps the dense math back to real words, predicting the next word in a sequence across the model's entire vocabulary. Moving right along to Section 2, Blueprints, the model configuration. Before a single drop of data hits your neural network, you need a blueprint. This configuration defines the exact shape and size of the neural network before any actual trained data is loaded into it. The pre-trained config base class standardizes everything. It tells the system the hidden underscore size, the num underscore attention heads, and how many num underscore hidden layers are required. Think of this literally like the blueprints for a skyscraper. It tells you exactly how many floors there are and where the load-bearing walls go, but it doesn't actually furnish the building. That separation is absolutely crucial. The architecture and the weights are two entirely distinct concepts. But of course, that brings up another real-world hurdle. Developers are constantly wondering what the canonical naming convention is for this vital blueprint file. You'll see different examples across all sorts of tutorials online, which leads to some very understandable confusion about what the system actually expects to find when it looks for the configuration. Let's definitively clear this up right now. While you technically can pass a custom file path named absolutely anything directly into the loader, standard directories and hub repositories strictly expect the file to be named config.json. The library actually has a constant hard-coded to look for config.json by default, so if you are ever publishing a model to share with others, you must use config.json just to ensure automated tools and loaders don't randomly break on you. Which brings us to Section 3, heavy lifting, loading those weights. Man, we have all seen this incredibly frustrating OS error. This happens when you only load the configuration skeleton, but leave behind the massive files containing the actual trained weights, which, by the way, are increasingly stored as secure, safe tensors. You just can't run inference on a blueprint. The weights are the actual knowledge of the AI. Traditionally, PyTorch used Pickle utilities to serialize weights into a bin file, but because Pickle can be pretty insecure, the modern standard is the safe tensors format. It's way faster to load and completely secure against malicious code injection. And when we say massive, we mean massive. To prevent your computer from just straight up crashing, Hugging Face automatically splits, or shards, checkpoints that exceed this 50 gigabyte threshold. Imagine trying to load a 100 gigabyte model into your RAM all at once. Yeah, no way. Your system would freeze and crash out of memory instantly. By sharding the weights into smaller chunks, the parameters can load in parallel. This keeps the shard counts manageable and drastically simplifies file management across distributed training environments. This right here is where Accelerate's Big Model Inference flexes its muscles. It saves memory by putting a fake skeleton on a meta device before carefully loading and dispatching the real weights. Without this, PyTorch would create randomly initialized weights in memory first and then try to load the pre-trained weights on top, meaning you'd literally need double the memory. By using a meta device, it basically creates an empty shell that takes up zero real data space. The actual weights are then loaded lazily and dispatched perfectly to your GPU, or if that fills up, to your CPU, and finally offloaded to your hard drive.
All right, Section 4, Dynamic Weight Transformation. What happens when things don't quite match up?
You see, there's often a huge disconnect between how a model is stored on disk and the optimized, fused structures it actually needs to run efficiently. For example, a checkpoint might store separate weights for different linear projections, like your Q, K, and V attention components, but the model actually runs way faster if those are fused into a single tensor. Or maybe you've got a legacy checkpoint using old naming conventions, but the modern architecture expects something entirely different at runtime. So how does Hugging Face deal with that? It handles this mismatch completely on the fly using scheduled, reversible conversion operations, things like chunking and concatenating as the weights are loaded asynchronously. The weight converter steps in and applies regular expressions to match the old checkpoint keys to the new model parameters. As the tensors are loading, it might chunk a fused tensor into smaller parts, it might concatenate several individual expert weights into a massive 3D tensor for a mixture of experts model, or transpose dimensions to fix layout mismatches. And it does all of this seamlessly while the model is actively loading into memory. Now you might be thinking, doesn't doing all that math during loading just destroy my RAM? Well, actually, no. Because this materialization is lazy and asynchronous, your memory usage stays highly efficient and rarely ever exceeds the actual model size. The loader scans the checkpoint just once to discover pattern matches, collects the required tensors as future objects, and submits them to a thread pool. A conversion operation just waits until exactly what it needs is loaded, performs the merge or chunk, and immediately discards the intermediate copies. So your peak memory really only bumps up by the size of the specific layers being transformed at that exact millisecond. It's brilliantly optimized. Finally, Section 5, Saving and Sharing Models. Let's get your work out to the world. Wrapping all this up is ridiculously easy. By simply calling save_pretrained, the library neatly packages the skeleton and the flesh together, and it even runs those complex dynamic weight conversions in reverse automatically. Remember how we chunked and concatenated weights during loading? Well, the weight converter tracks all of that. When you save, it runs the entire process backward, unpacking and splitting the tensors so they save exactly how the broader community and other frameworks expect them to. Then, with a single call to push__hub, your configuration, your safe tensors, and your dynamic mapping code are securely uploaded to the Hugging Face hub, completely ready for the next person to run from _pretrained. So, now that you've got a solid grasp on the powerful mechanics actually running under the hood of this massive ecosystem, the only question left is how you're going to use it. You've seen how Hugging Face flawlessly abstracts away the immense complexity of architecture mapping, lazy memory loading, sharding, and real-time tensor transformations. It literally puts the power of supercomputing AI directly into a single line of Python. So, armed with all this knowledge, what incredible tool are you going to build next?